So yeah, today I'm going to talk about a problem which really is used a lot in numerical weather prediction, but it's a lot bigger than numerical weather prediction. Numerical weather prediction is already big, but this is a very generic problem. It's a problem that is relevant to data scientists, I think. It's a problem where you want to make predictions, but your data is very sparse. You also have a lot of prior information about the data. You know that it comes from a model. So it's time-evolving data that comes from a model that you know something about. The model, however, is not a good model for making predictions. So we're going to be looking at, chaotic models. Chaotic models are not good at making predictions. Small uncertainties in your information about current state can lead to large uncertainties in predictions. So we want to try and combine these two pieces of information. We want to combine the model that we have and the data to try and make better predictions. So I'm a mathematician, I have to warn you. I tried to scrub as much math from my slides as I could, but some things are left over. In particular, the first slide has math. So I'll give you a toy example of a model which fits into this framework. This is called the Lorentz equations. It's a three-dimensional ordinary differential equation. So it's just a point in three-dimensional space moving around. The velocity of the point is a function of where the point is in space. It has these three parameters, sigma, rho, beta. And for certain choices of these parameters, this is a chaotic model. And that means that you can have two initial conditions of the equation that are close together. And if you watch them evolve in time, they'll separate and have nothing to do with each other anymore. So there's a large decay of correlations in how close things are together. So you can think of this as kind of a toy atmospheric model. You can write down honest-to-God models for the atmosphere, do a very crude approximation of it, and arrive at something like this. So even though it's a toy model, it does have something to do with real models, like atmospheric models. So I'll just show you the plot of what a single trajectory of this model looks like so you can understand what it means, how is data evolving in time. So I started at one point, and this is what happens as I evolve in time. It'll trace out a shape which might be familiar to some of you. So this is called the butterfly attractor, or the Lorentz attractor. So essentially what happens is no matter where you start, you get sucked into this lower dimensional part of your three-dimensional space, which has a very complicated structure. That's this butterfly shape. And every time you every time you get close to the two lobes, it's extremely difficult to know which direction you'll take. It's extremely hard to predict whether you'll stick on the left or go over to the right. So this is what gives you this kind of barrier to prediction. Okay, so now I want you to imagine that this is what's happening in reality, and this is the thing that we want to predict, but we don't actually know exactly where it started. We know approximately where it started. So what happens if we only knew approximately where it started? For instance, if we had 10 different ideas of where it was, and we started those 10 ideas and flowed them forward in time. So this is maybe 10. So they do roughly the same thing until they reach the butterfly. And once they get onto this attractor, their behavior becomes almost random. They completely forget that they ever had anything to do with each other. So there's this barrier to making predictions. So if you look at the dots, they're just wandering randomly on the attractor now. So they have nothing to do with each other anymore. So this is the barrier to predictions that you have in a model. This is not something that's special to these chaotic models. This is just a property of randomness. So this is a very generic problem for any model that has some kind of prediction barrier. This is kind of just a nice way of illustrating it, that it can actually happen in deterministic models where there's no randomness. Okay, so the model by itself is not great for making predictions. So what if we had data from the one true trajectory? Maybe not the whole point. If we had the whole data point, then we wouldn't really need the model at all. So what if we just had part of the data point? For example, suppose that we just observe the x variable. Out of the three variables, we just observe the first. And you observe it with a bit of noise as well. You observe it every tau seconds. So every tau seconds, you get a new data point, and it's perturbed by some noise because your measurement is kind of noisy, and you want to try and use this additional data to make your estimate better. So can we take those 10 ideas that are evolving in time, the ensemble of different predictions that we had, and blend them with the data in such a way that they make the prediction better? So what we're doing here, so each one of these dots is one of my predictions. Every tau seconds, I'm assimilating a new data point. The blue curve is the true thing that's producing the data. What happens over time is that the dots all converge to each other, and eventually they converge to the right thing and stay there forever. So this is called data assimilation. You have a problem where separately the two things don't have enough information, but if you combine the two pieces of information in the right way, you can make good predictions. You can track the signal. So it's not just a prediction problem, because to do this, we need the data now. So we're not really making predictions. It's more like we're making spatial predictions. We have incomplete data, and we want to know what are the other data points that we can't see. And you can also think, if we knew where we are now, then we can use that fact to make a better prediction in the future. OK, so the point of this talk is to try and so this is a toy model that I've shown you. It's not just for toy models, though. This is huge business. So techniques like this have been used for numerical weather prediction basically since computers have existed, so for 70 years or something. The methods that they use are extremely ad hoc to begin with and have been getting more and more sophisticated over time. The models that they use are not three-dimensional at all. They're extremely high-dimensional. So you can think of them as you take a PDE, which is describing maybe a section of the ocean or the atmosphere, a partial differential equation. You discretize it to a level of resolution that you care about. We only care about what the ocean looks like, say, at 100 meter by or 100 kilometer by 100 kilometer mesh. This gives you something that is extremely high dimensional if you do it for a large space of the Earth. And it's not just that you care, there's so many different variables that you care about at each point in space. You care about pressure, you care about temperature, you care about ocean currents. This gives you an extremely high dimensional model. It's also a turbulent model, it's a chaotic model, in the sense that even if it wasn't random, small differences in initial conditions would lead to large differences further down the line. When they use these models operationally, they actually put randomness in there to just account for everything they don't know. So everything you don't know in your model, all the effects from the small scales that you can't possibly account for in your model, you just model it with randomness. You just replace your uncertainty with true randomness. So in operation, these models are huge dimensional, very hard to predict, often genuinely random. The observations that you make, they're things like, I drop a buoy in the ocean, I let it float around, the buoy is GPS activated. What does that tell me about the ocean currents? I have weather balloons that move around that make measurements of pressure. They give me extremely sparse data measurements because it's the pressure at one point in space. You have satellite images that take low-resolution images of the Earth. It's not a great data point because there's clouds and things that get in the way of the stuff you really want to see. So it's obscured, it's sparse, it's noisy. But we want to try and combine this extremely sparse, very diverse amount of data with the model. So you should think of it as very sparse. It's actually quite accurate in the sense that when you make measurements, the noise isn't that huge. There's things that stop you from measuring something, but you don't really call that noise. You just say your measurement isn't available in that sense, like a cloud, and you just throw the data away. And the observational data is not just observe the x variable, it's observe some complicated function of the variables, like what effect does it have on a buoy floating in the ocean. Okay, so for the next 25 slides, roughly, I'm going to tell you a bit about the math behind data assimilation. So what is the real mathematical problem that you're trying to get at when you write down an algorithm to achieve this task? I'll explain what happens in the linear model scenario. This gives you something called a Kalman filter, which I guess some of you have heard of before. And then what happens in the nonlinear model scenario. So Kalman filters have existed for a while. They came out in the 60s and have been hugely successful. For numerical weather prediction, they're not linear models at all, and you need to use ideas to try and extend linear ideas to nonlinear models. So the last part of the talk, I'll try and tell you about that. So the math of data assimilation. So suppose that we're tracking a d-dimensional vector, un, whose motion is governed by a discrete time random dynamical system. Okay, what does all this mean? So un is a vector, is evolving in time. N is the index, the time index of the vector. A discrete time random dynamical system means you take your point at time n, you apply some function to it, which takes it somewhere else, and then you add noise. So a dynamical system is if you just applied a function to it. A random dynamical system is if it's a random function. So this is just a very specific example of a random function. You move your point around, and then you add noise to it. So it's a very simple model, but actually a model that's used a lot. So you could think that in numerical weather prediction, you often have this map. Whoops. This map psi is saying, solve my ODE for some amount of time. Put in un as the initial condition, and then solve it for tau seconds. What happened to that point in tau seconds? That's the output of psi. The noise that you add on is to account for the fact that your model wasn't perfect. You have some kind of uncertainty in your model. So you add noise to reflect that you're not actually that certain about your model. So psi n, or eta n here, is, I'm just going to say it's an IID source of Gaussian noise. Probably IID is not the best way to model this because uncertainties that you have in your model would be correlated in time. So it's not the best model, but it's a good starting point. In the Lorentz example, we just took this to be 0. There was no noise in the actual model here, but you don't have to take it to be 0. You could put model in there to reflect uncertainty. And psi, we're always going to think of that as a deterministic map. So the problem is the initial state, u0, is not exactly known. For instance, we might just know that it's distributed like some Gaussian. So you could think that we know the mean of where it is, and we know that it has some spread. So what happens as we evolve in time? So in that animation I showed you, you could imagine that we had this little tight Gaussian, and those 10 points that we had were samples from that Gaussian. And then as they evolved in time, they spread over the whole attractor. So if you imagine what happened if we took this Gaussian and pushed it forward in time, it becomes a distribution spread across the whole attractor. And you've lost all your information. You just know that you're somewhere on the attractor. But every point is always somewhere on the attractor, so you've basically lost all your information. We also have data. So we make partial noisy observations at every time step. So the data is some vector called Zn plus 1, living in probably a much lower dimensional space than the whole state, because it's a sparse data point. It's some function of the true state, and we have observational noise. So what we want to do, how do we combine the two pieces of information? So the correct way to do it, probabilistically, is to define the conditional distribution. Okay, so what do I mean by that? So if I take a randomly distributed u0 and I push it through my model, I get a random variable. I want to condition that random variable on the data that I have. This gives me a new random variable, but hopefully one that has more information than if I didn't condition on the data. By conditioning on the data, I can rule out things that I know didn't happen. I still don't know exactly what happened, but hopefully I can reduce my uncertainty by conditioning on the data. So that's what this conditional distribution does. So the un is a random variable. We would like to know the conditional distribution of un given all the data up to now. So not just given the latest data point, given every piece of data that we've observed so far. So we can actually interpret this, or we can define this conditional distribution nicely using Bayes' formula. So Bayes' formula, sorry, math. How do we use Bayes' formula? So in the first line, all I'm doing here is I'm splitting off the latest observation that you make. So this collection of all your data points, Zn plus 1, you split it off into Zn and then the latest data point. Then we're going to use Bayes' formula just on that latest data point. So leaving the capital Zn in the conditional part of the conditional distribution. That allows us to factorize this as a product of three things, well, a ratio of three things. The first term that appears in the second line is called a likelihood. It's the likelihood that you would have observed that observation given that it was at UN plus 1. The next term is what we call a prior. This is how likely is the state to be at UN plus 1 just given all the past data. So not given the new information that I just got, just given the past data, how likely am I to be at UN plus 1? So this is my prior information. In the denominator, that's just a normalization factor. Doesn't matter so much. It's just a constant. We care about how this depends on UN plus 1, because that tells us where the state is. So the normalization factor doesn't depend on UN plus 1. It's just a constant. So you should think about this as this conditional distribution is really proportional to these two factors, a likelihood and a prior. So we can use this idea to perform an update procedure. So if this doesn't make much sense, I'll give you a picture which hopefully will make it make sense. So this blue circle here represents my uncertainty at time n. So this is the distribution conditioned on everything I've observed up to time n. This is where I think what I know about the true state at time n. So what do? The first thing I do is I apply my dynamics. So I take that initial uncertainty and I just flow it forward using my dynamics, so using this random dynamical system. So when you flow something forward through a map or dynamics that has uncertainty in it, your uncertainty will grow. You'll spread out even more, because small uncertainties in the initial condition lead to large uncertainties later on. So we had our small uncertainty and we got a bigger uncertainty. So this is our prior knowledge of where we are at time n plus 1, not given any extra data yet. So this is what you call a forecast distribution, because you're just taking what you knew a second ago and you're making a forecast using only the model. Now we make an observation. Say that we just observed the x variable. So we only know where it is on the x line. So really you should think of that observation as like a line extending infinitely up the y-axis, but you know it's at that point. Well, it had noise, so you know it's near that point. So to combine those two pieces of information, essentially you take your forecast distribution and you re-weight it with this likelihood factor. The likelihood factor is how likely am I to be at some point, say this point, given that this was my observation. You're extremely unlikely to be here if you observed that your x value was here, but you're much more likely to be here. So you re-weight your forecast distribution using the observation. So this green distribution is the re-weighted distribution. This is your new estimate, or all the information that you have about the state at time n plus 1, given all the data up to n plus 1. So in Bayesian terminology, this is called a posterior. You have a prior, which is what you thought before you included the data, and then you have a posterior, which is what you thought after you included the data. So this is our posterior. So this cycle, this is your new starting point once you get the next observation. So this creates a cycle. So this is called the filtering cycle. So in the linear model scenario, everything has a formula, which makes this problem very nice. So what do I mean by that? So you have something called the Kalman filter in the linear model scenario. So when I say linear model, I assume that the map psi, that deterministic map, is just a matrix. So the evolution is linear for the model. The observation function, h, I'm assuming that's linear as well. So that's also just a matrix. You can think of it as like a low-dimensional projection, if you like. So you just project onto some of your data points, or you mix up some of your data points, but it's still just a linear map. Under this assumption, the conditional distribution, or the conditional random variable un given Zn plus 1, is a Gaussian. So when you take something that's originally a Gaussian, you flow it forward under your model, it's still a Gaussian. It's just a Gaussian with a different mean and covariance. You then condition on data, it's still a Gaussian, as long as that data was also Gaussian. So the nice thing about assuming everything's linear is that the distribution that you care about, the posterior, remains a Gaussian. The nice thing about Gaussians is that they're completely characterized by their mean and covariance. So to understand this distribution completely, you just need the formula for its mean and covariance. You can show that the mean and covariance satisfies a recursion formula. So if you knew the mean and covariance at time n, you can figure out the mean and covariance at time n plus 1. So these are the famous Kalman formulas, Kalman update formulas. So it's basically telling us that it's an extremely intuitive formula. Why is it intuitive? So you have two pieces of information that are telling you what your new mean should be. They should be your old mean pushed forward under your model, and also your data, your new observation point. Intuitively, or at least if everything was one-dimensional, you would expect that your new mean would be a convex combination of these two things. And it should be some kind of optimal convex combination. That's exactly what we have here. The new mean is a convex combination of what we would guess just from the model and what we think from the data. It's kind of a complicated convex combination because the two things live in different spaces. So you need matrices to make sure that you end up in the right spaces. The formula for the covariance is not so important. Just know that there is a formula for the covariance. So this matrix Kn plus 1 is called the Kalman gain, and this is really the correct choice of convex combination for your model and your data. It's determined by the covariances in your observation and in your forecast. So I'll go back to the picture to explain what I mean by that. If you look at this slide and imagine where should my new mean be, I think it's a convex combination of these two things. The amount that I move by will depend a lot on how much I trust each of those two things. If my observation was perfect, if the noise was 0 or extremely small, I would really move exactly to x. If my forecast was extremely spread out, I wouldn't really trust my forecast that much. If I had a huge covariance in the forecast, I wouldn't trust it that much. So I would trust, if I'm thinking about what kind of convex combination I want to take between the observation and the forecast, in that scenario, it would be for the observation. But you might have situations where the forecast is extremely tight. So where this blue circle here would be really small, and you would trust your model a lot. And your observation, maybe you don't trust it at all. And in that case, you'd want to take a convex combination which is more in favor of the model than the observation. So there's an optimal choice, or a correct choice of convex combination, which is really just a function of these two covariances. The covariance in your observational noise and the covariance of this blue circle, which I'll call the forecast covariance. How much do you trust your forecast? So it's going to be an important idea when we start looking at more complicated things than Kalman filters. Okay, so that's Kalman filters. So what do we do when we're not linear? So in particular, if we just don't assume that psi is linear anymore. It's not a matrix, it's a function. So the simplest thing that you can do in meteorology, it's called the 3D VAR algorithm. They started using it in the 60s, and the US still uses it. Nobody else uses it, but the US still uses it. It's a really simple idea. You're basically trying to get a state estimate, Mn, using something like a Kalman update formula. So we like this intuition. We like the intuition that our new estimate should be a convex combination of the two pieces of information we have, the forecast and the observation. that intuition still makes sense when the model is nonlinear. You can still take your old estimate of the state, apply your nonlinear map to it, and get a new guess of what it was just based on the model. The problem is that we no longer have an optimal choice of the convex combination. That was something that we had because everything was Gaussian. We knew what the covariances were. We could optimally pick which one should be, or how much we should trust the forecast and the observation, because we knew how much we trusted our forecast. In a nonlinear situation, you don't really have that. You don't have formulas for covariances. So what 3D VAR says is it just says, hope that there exists such a K and find it by tuning. Or maybe you don't even need to tune that much. Maybe it'll work without any tuning. So hope that you can pick some convex combination of your mean and your observation in such a way that you track the truth well. And this is really kind of you're breaking away from the Bayesian situation because you're only producing the mean here. You're not producing anything about a distribution. You're just producing one vector, which is tracking the state. That's all. So the animation that I showed you earlier, this is actually 3D VAR. So each one of these things is a different M. There's a different thing tracking the state. And you can see, well, so I didn't tune this whatsoever. I just picked, so the H is my observation function. It looks like that because I'm only observing the X variable. And then I just picked, well, let's see if 111 works. And it works pretty well. So a lot of the time, you don't actually have to do any tuning to get these things to work. So we had these 10 different things, which started off not very good. But by just assimilating the X data in a really crude way, we're able to make them synchronize. So also notice something, which is that all the particles, all the different state estimates, before converging to the correct signal, they converge to each other. This is kind of a bad thing. Because if you imagine that you were running 100 predictions and all of them did the same thing, you would be assuming something about your uncertainty. You would be thinking, well, maybe if all of my predictions are the same, they have to be close to the truth. If there was any uncertainty, they should be doing different things. The fact that they all jump on top of each other tells me something about how certain I should be about my prediction. But actually, they jump on top of each other, and they're not on the true signal. So that's a problem with 3D VAR. So you might be able to synchronize eventually, but you don't necessarily know too much about uncertainty quantification. For the 3D VAR algorithm, you can actually mathematically prove that it's accurate. So some of my research is to prove things about algorithms like this. You can mathematically prove that for quite large classes of models, it's accurate in the sense that if you let it run for long enough, for even not great choices of K, you will synchronize with the true state. But it assumes a few things. It assumes that you're observing enough of the variables, so your observation operator is not too sparse. It can be quite sparse, but it's not too sparse. You also need to assume that the observational noise is not that huge. So the theorems that you end up proving are typically in the long time limit, you converge to some kind of band around the true trajectory, and the width of that band is proportional to your observational noise. So if your obs noise was huge, then that band would be useless. So 3D VAR is accurate. When obs are sparse, you can't necessarily expect accuracy. You might expect that there's lots of different possible answers, and 3D VAR just picks one of them. Maybe all of your copies of 3D VAR pick the wrong one. So you want to be able to say that in situations where you can't necessarily figure out everything about the true trajectory, maybe you want to say something about the posterior instead. Does 3D VAR help me with that? It turns out it doesn't. It doesn't have any uncertainty quantification at all. It doesn't tell you anything about the covariance of your posterior. It doesn't tell you anything about the distribution whatsoever. It just gives you one state estimate. So we would like an algorithm which, in addition to a state estimate, told us something about uncertainty. So we want something that tells us about the posterior and not just gives us a state estimate. So this is what something called an ensemble Kalman filter does. So an ensemble Kalman filter, it uses an ensemble of particles that are interacting with each other. And they're trying to look like samples from this distribution. So in particular, if you looked at the mean of your ensemble, that should be close to the mean of this distribution. If you looked at the covariance of that ensemble, it should tell you something about the covariance of this distribution. So the EnKF, as it's called, this is what Canada uses, and it's better. And Europe uses it in combination with a few other things, and Europe are kind of state-of-the-art at weather prediction. Okay, so how does EnKF work? So you want to maintain this ensemble. It's an ensemble, just like in that picture, we had an ensemble of state estimates. Now we have an ensemble where all the particles are coupled together. So we want them to represent the whole posterior and not just the mean. Each particle is updated just like 3D var. So you find some sort of convex combination for each single one of your particles. You find a convex combination of what you predict it should be. So you take your previous particle, you apply your nonlinear dynamics to it to see where you predict that a particle would go just based on your model. You combine it with data, and you want to find some sort of optimal combination of these two things. Remember that to pick the right convex combination, you want to have some knowledge of how certain you are about the two pieces of information. You want to know something about the covariance of your forecast distribution and the covariance of your observational noise. We know the covariance of our observational noise. That's nothing to do with nonlinearity. We don't know anything about the covariance of the forecast. But if we have an ensemble, then we do. If we have an ensemble of particles, we can use that ensemble to say something about the covariance. So you take your ensemble, you flow it forward under your model. This tells you something about how much you trust your model. It tells you something about the covariance of your model. So you take that empirical covariance from the ensemble, and you feed it into the Kalman formulas as if it was the real covariance. And that's what you do. That's an ensemble Kalman filter. Okay, so I'll give you the same picture, but with an ensemble rather than actual distributions, so you can understand the idea. So you start with an ensemble, which represents your posterior at time n. So think of this as like samples from the real distribution. You apply your dynamics to all of them. So each one of those points, you just apply the dynamics, and it goes to one of those points. This tells you, it gives you some kind of approximation of the forecast distribution. It gives you an empirical approximation of the forecast distribution. In particular, you can use the empirical mean of this to figure out what is the mean of the forecast distribution, or approximate it. You can use the empirical covariance to figure out how much you trust that distribution. You then make an observation, and you shift each one of those particles using the Kalman formula. And this gives you a new empirical representation of a posterior. So Canada uses this. They use it for operational numerical weather prediction, NWP, numerical weather prediction. There's an amazing thing about EnKF. So I've sold this to you as a kind of a sampling algorithm. It's like we're trying to represent a probability distribution using samples. For numerical weather prediction, you're trying to represent a random variable which is enormously high dimensional. It's 1 billion dimensional. You need a lot of samples to represent something that is 1 billion dimensional. The amount of samples that you need typically scales exponentially with the dimension of the state. So you would need exponential of 1 billion variables to come up with a good representation of this measure. Canada uses it with 100, and it works. So it's an amazing and mysterious thing about the ensemble Kalman filter that allows you to use it for extremely high dimensional models with a very low number of particles. The intuition you should have is that a lot of these models are not as high dimensional as they seem. An example of that So the Navier-Stokes equations, it's an infinite dimensional PDE. You can actually prove that just like the Lorentz equation, it has a finite dimensional attractor. There's some finite dimensional subspace of an infinite dimensional space that your dynamics always get sucked into. Most of the dynamics are just dissipation. They're just high energy things that go away in time. The interesting things that are hard to predict happen on a finite dimensional space. EnKF is good at finding this finite dimensional space. That's how you should think about this. So this is another line of direction for mathematicians, trying to figure out how you can use the fact that these models have effective lower dimensionality to prove that EnKF will really work. And the intuition is that this covariance, the forecast ensemble, it doesn't explore the boring directions of your enormous space. It only explores the directions where your model varies the most, because that's what covariance does. So just like in that picture where we had the blue ellipse, the covariance stretched out in the directions where you had the most forecast variance. In an extremely high dimensional state, you might only have forecast variance in some of the variables, in a much lower dimensional set of variables. So I'll show you an animation that'll convince you that EnKF is not perfect. This is another toy model. It's called I call it the Sombrero SDE. So probably a lot of you don't know what SDEs are, but that's all right, I'll explain it to you. You should think of this model as a point living in that sombrero. What the point wants to do is move to the rim of the sombrero. It wants to minimize its height on the sombrero. So it wants to fall just like a marble. If you dropped a marble in the sombrero, then it will fall down to the rim. The marble has its own inherent vibration. It's got noise, which means that even though it falls down, once it gets there, it rattles around a lot. And it'll rattle around the sombrero. So if you looked at this thing from above, it just looks like a kind of noisy thing walking around a circle. So it's a two-dimensional state. Well, you can think of it as a two-dimensional state because it's just a noisy thing walking around a circle. So what happens if we only observe the x variable? So we want to try and track this thing which is moving around the sombrero, and we're only observing the x variable. So this is EnKF with lots and lots of particles for a two-dimensional system. The red star is the true thing which is producing the observations, it's producing the data. And what we'll see is that over time, your ensemble clusters on the truth, which is good. So there's a few that get left over on the top, but eventually they all get sucked down. The reason for this is that non-Gaussian states for this ensemble are very unstable. So if you had an example where your particles were spread out and they looked like they were samples from not a Gaussian thing, that would be very unstable and it would pick some kind of Gaussian. So even though they started off spread out, they got sucked down to the right thing. So you imagine what the system is seeing. It's observing the x variable just there. It doesn't actually know which branch it's on. It doesn't know if it's on the top or the bottom. So it gets sucked down because non-Gaussian things are unstable for an ensemble Kalman filter. I'll show you the exact same thing with the exact same trajectory of the truth. All we're doing is using a different noise in the model for making predictions, which is something that would happen in real life. So you'll see that the red star does exactly what it did before. I mean, I guess you won't remember what it did before, but trust me. All we're doing is using different noise in the model for the ensemble for the forecast prediction. It gets sucked to the wrong thing. So you can think of this as a problem with uncertainty quantification. In both of those two situations, you would make a prediction and you would get some certainty about it, and in both of them you'd be wrong. So in the first one, you'd actually be making the right prediction, but you wouldn't be capturing the posterior correctly. The posterior should be concentrated on the two branches because you don't know which one you're on. EnKF will kind of pick the Gaussian of best fit. So EnKF is not good at finding very non-Gaussian posteriors. So the last thing I'll show you is something which is much better. I won't tell you anything about this because I don't have time. This is a particle filter. So EnKF is, it has the ambition of being a sampling algorithm, but it's not a sampling algorithm. It's not actually sampling from the real posterior. It's sampling from some kind of Gaussian approximation of it, which makes it a lot cheaper and it makes it work really well in high dimensions. A particle filter is something which actually does sample from the posterior. So you can see that it does the right thing. The particles now hover on the two branches. So the four things that I've introduced, well, the last one I haven't really introduced, essentially what researchers are trying to do now is they're trying to expand, figure out in what directions these things don't work, and in what they do, and see if they can break the barriers between them. So Kalman filter has the obvious barrier of only working for linear models. 3D VAR works for nonlinear models, but has terrible uncertainty quantification, no uncertainty quantification. EnKF is extremely efficient, works in high dimensions, gives you some UQ, uncertainty quantification, but not for non-Gaussians. Particle filters, this thing that I just showed you on the last slide and didn't tell you anything about, these really give you intelligent information about a posterior, but they're horribly inefficient in large dimensions. So this intuition I gave you that the number of samples that you need scales exponentially with the dimension, that's really true for particle filters. So what people are doing these days in research is to try and sort of blur the lines between these algorithms. See if you can take some intuition from EnKF and apply it to particle filters to make particle filters give you intelligent information but work better in high dimensions. Okay, thank you for listening. I put all my slides on my website if you want to see those pretty animations again. Thanks.
So David will be available for office hours in the room below this one. So you can find him there, and we'll have 5 minutes while we set up the next speaker.